I wanted to start off this section talking about ways in which nuclides can decay. We've already talked about some of these particles, but I want to talk more specifically about how they can decay. So one of the first ways in which we can talk about nuclides decaying is via an alpha emission or alpha decay. As you know, alpha decay is a loss of a helium nucleus, which has 2 protons and 4 total for a mass, or 2 neutrons. An example of this would be a reaction of, for instance, polonium-208. Polonium has a mass of 84. And if this decays by alpha decay, then we're going to get an alpha particle, which is 2 and 4. And then you should be able to decide what the next product is here in this reaction, right? So 2 plus something has to equal 84, so it's an 82 down below. And up above, 4 plus something must equal 208, so that must be a 204. I then look at a periodic table to find out what has 82 protons, and according to the periodic table, that is lead. So that is a balanced chemical reaction, and it is an example of alpha decay. We can also have beta decay. Beta decay is a loss of essentially an electron. An electron we write as B with a -1. It has 0 mass. And so an example of this might be something like iodine 131. Iodine 131 has 53 protons. And so if we are going to lose a beta particle, -1 and 0, then -1 plus something must be equal to 53, so that must be a 54 down below, and we have 0 change in mass, so that must be a 131 up above, and 54 for a mass number, for a atomic number, is the atomic number of xenon. So when does this happen? We get beta decay primarily when we have a neutron-rich nucleus. In essence, what we're doing here is we're converting a neutron to a proton. And so when we take a look at our band of stability, if we sit above that band of stability, then we are going to convert a neutron to a proton and bring us closer to being back into the band of stability. And so that's why it might beta decay. When do we get alpha decay? Usually we get alpha decay when we're looking at very heavy particles. They may be in the band of stability and they're just trying to fission their way down to iron 56, or maybe even lead 207 or 206, which we'll see an example of that. But usually with very heavy nuclides, oftentimes in the band of stability. We can also get gamma decay. Gamma decay basically is, an example of that might be something like barium-137, and barium has an atomic number of 56. But if you recall, a gamma particle has 0 and 0, so 0 mass and 0 charge. So what you end up getting is still 56 with a barium on there, still at 137. So there's really no change, except for I'm going to put a little asterisk on that initial barium, because typically what happens is you've got an excited state of a particle, and it's just going down to a ground state. So it's just losing some excess energy without giving off any particles. The next one is what we call a positron emission. Positron emission is a beta particle, but instead of it being an electron, it's a positron, so it has a +1 charge but no mass. An example of this would be, say, something like boron 8. Boron 8, if it's going to positron emission, that means we're going to get a beta with a +1 and a 0. So we're going to end up with a 4 down here and 8 up above. And when we look at the periodic table, we see that 4 protons is beryllium. When does this happen? You'll notice that what we're doing is we started with 5 protons, we went to 4 protons. So we're keeping the mass the same, but we're decreasing the number of protons. So we've actually converted a proton into a neutron. And this will happen if you have a proton-rich nucleus. And those typically are seen below the band of stability. And so that's when we get positron emission. Positron emission and electron capture are two different processes, but they accomplish the same thing. Electron capture might again exist for, say, something like boron 8. So we get a boron there, and if we get electron capture, then what we're going to do is we are going to add to this an electron. And what do we end up getting from that? So 5 minus 1 is 4, 8 plus 0 is still 8, so we still end up with the same product that we had before. So electron capture and positron emission give us the same result. It's just that in positron emission we're taking a neutron that's in the nucleus and we are converting that into a proton and an electron in essence, and booting out that electron, if you will, in the form of a positron. In electron capture, we're taking one of those electrons from an inner shell, so maybe from the 1s orbital, and we are bringing that electron into the nucleus, combining it with a proton, and making a neutron from that. And so those are our 5 different kinds of radioactive decays. Here is an example of the decay of uranium-238. Some of these happen quickly, very quickly. Some of them take hundreds of thousands of years. And so I've done the first couple for us here. I started with uranium-238, and we did alpha decay. And if you go alpha decay, again, you're losing 2 protons and 2 neutrons, or 4 mass numbers. So we went from 238 to 234. We have 90 protons now, and if we look that up, that is thorium. That undergoes then beta decay, and beta decay again is increasing the number of protons to by 1 to 91, but the mass stays the same, so 234. So we end up with protactinium, Pa, for the next piece. You should be able to then, from here on out, tell me what kinds of decays are occurring at each of these arrows. And so take a little bit of time to do that and come back. And now that you're back, you should be able to tell me that as you go from 91 protons to 92 protons, that must have been a beta decay. From 92 protons to 90 protons must have been an alpha decay. From 90 to 88 must be another alpha decay. 88 to 86, alpha. 86 to 84, alpha. 84 to 82, alpha. 82 to 83, beta. 83 to 84, beta. And 84 to 82, alpha. And 82 to 83, beta. 83 to 84, beta. 84 to 82, alpha. This follows the degradation or decay series that you'll see in figure 21.9 of your textbook.